Welcome to Next Generation Game Engines, where we dive into groundbreaking innovations in gaming. Players are always asking for new versions of their favorite games, like Titanfall 3, Counter-Strike 3, Crysis 4, Grand Theft Auto 6, Hades 2, Hollow Knight Silksong, Frostpunk 2, and so on. But does it make sense to keep asking for sequels? What would a new version really offer? To answer that, we need to look at game engines, the backbone of every modern game. While some new engines are in development, many of them bring only incremental innovations. Take Unreal Engine 5, for instance. Its big claim to fame is Nanite, a technology that scans real-world objects and brings them into virtual spaces. But here's the catch. This innovation doesn't really help with fantasy games, where objects are often purely imaginary and can't be scanned in the real world. So, are there any truly groundbreaking features on the horizon to make these sequels worth it? Or are we stuck with the same old concepts? Let's find out. First, let's explore the technologies behind next-generation game engines and take a closer look at what truly makes them useful in modern games. The lighting in modern games has become stunningly realistic, as demonstrated in this Lumen demo. Lumen dynamically simulates how light interacts with environments in real time, showcasing effects like sunlight streaming through windows and subtle shadows dancing across uneven surfaces. From glowing reflections on shiny objects to intricate lighting in darker areas, the demo perfectly illustrates how Lumen brings vibrant, dynamic lighting to life. To dive deeper into the science behind light, ray tracing takes realism to the next level. This technique, as explained here, replicates the natural behavior of light by simulating how rays travel through space, bounce off surfaces, and interact with materials. The demo showcases lifelike reflections on water, glass, and polished metal, immersing players in a world of visual authenticity. Together, these technologies push lighting in games into new realms of realism. Using advanced physics simulations, here we see a character walking through a swamp. When the character pushes against the floating tree trunks, the trunks move accordingly, creating a dynamic and responsive environment where objects react to the player's actions, enhancing immersion. With procedural destruction, the scene shifts to a spaceship hovering above water and firing on a coastal village. As the bullets strike the buildings, each impact causes a unique destruction event, with the structures collapsing in different ways every time. This variability in destruction adds realism and makes the environment feel alive, as it responds unpredictably to the player's actions. Finally, photogrammetry is used to create an abandoned building environment so lifelike that it feels like real-world footage. The textures and details are meticulously captured, making the space appear incredibly realistic. The graphics are so real that they can hardly be distinguished from reality, with only pop-up messages reminding us that it's a game. Next-gen game engines also bring features like renewable environments, where ecosystems evolve in real time, and aging and soiling of materials, creating more believable worlds. As time passes, surfaces degrade, rust forms on metal, and dirt accumulates on objects, further immersing players in dynamic, ever-changing environments. These details not only enhance realism, but also deepen the connection between the player and the virtual world. Rendering techniques play a crucial role in modern game development. Multi-threaded rendering optimizes performance by distributing rendering tasks across multiple CPU cores, allowing for smoother gameplay and higher frame rates. This approach ensures efficient use of hardware resources, enabling games to handle complex scenes without significant slowdowns. Cloud-based rendering, on the other hand, leverages powerful remote servers to process graphics. This technology allows devices with limited hardware capabilities to deliver high-quality visuals by streaming rendered frames over the internet. However, cloud-based rendering has its drawbacks. It is not suitable for fast-paced first-person shooter games due to latency issues and the need for millisecond precision in calculations. Despite these limitations, cloud rendering can still optimize specific aspects of games. Elements such as landscapes, distant scenery, and dynamic weather effects can be rendered in the cloud, as they don't rely on immediate responsiveness. This hybrid approach not only balances the strengths of cloud rendering with the real-time demands of gameplay, but also reduces the load on the player's processors, enhancing overall performance and accessibility. However, it requires a stable and fast internet connection to function effectively. A cutting-edge dynamic universe and procedural generation system empowers developers to create vast, seamless worlds with remarkable efficiency. This technology generates everything from outposts, villages, and cities to planets, moons, space stations, asteroids, and an entire universe. Developers set parameters, such as terrain types, architectural styles, vegetation, and weather patterns. And the system dynamically combines these to produce highly detailed, diverse, and realistic environments. In one example, a planet is procedurally populated with over 3,000 locations, including villages and cities, each featuring unique layouts, ecosystems, and architecture. This approach balances handcrafted precision with procedural variety, enabling expansive worlds to be created with ease. Seamless streaming technology ensures that players can explore these vast worlds without interruptions. In the scene, the camera, representing a player, flies through space toward a planet. As it nears, a space station in orbit appears in stunning detail. The player's perspective shifts toward the planet's surface, diving into its atmosphere and revealing a sprawling city below. Flying over the city, the camera descends until it enters a building, all without a single loading screen. This real-time loading of objects, terrains, and structures creates an uninterrupted, immersive experience. These systems don't just build static environments, they craft living, responsive worlds. From dynamic weather patterns to evolving ecosystems, the environments react to players' actions, making every interaction feel meaningful. Together, procedural generation and seamless streaming pave the way for limitless exploration and redefine what's possible in gaming. Artificial intelligence is shaping gaming with smarter, more immersive experiences. Machine learning adapts gameplay to players' styles, adjusting difficulty and NPC behavior. Procedural content generation creates dynamic worlds and fresh missions, ensuring no two playthroughs are the same. Real-time crowd simulation adds realism, with thousands of characters moving and interacting naturally. Advanced NPCs and digital humans bring lifelike behavior and expressions, making every encounter feel real. AI is enhancing the depth and realism of games, from dynamic environments to believable characters. Server meshing connects multiple servers into one gigantic virtual server, letting thousands of players share the same world. Released as an alpha in Star Citizen 4.0, it's already working. Players can team up for missions, explore vast areas together, or engage in massive battles against each other, all in the same seamless universe. This technology could change online gaming forever. Hardware challenges and the future of gaming. Next-generation gaming engines unlock incredible possibilities, but hardware remains a critical bottleneck. Even state-of-the-art GPUs struggle to keep up. For example, in Cyberpunk 2077, an RTX 5090 achieves only 28 FPS at max settings without upscaling. AI tools like DLSS 4 boost this to 290 FPS in 4K, but the majority of these are AI-generated fake frames. These frames improve smoothness but don't reflect true GPU rendering. For gamers, the priority is clear: low latency and true native performance for real-time gaming. While AI solutions help, they're temporary fixes to deeper hardware limitations. Without breakthroughs in GPU architecture, the future of gaming risks outpacing the technology behind it. NVIDIA CEO Jensen Huang highlighted the issue, stating, "The semiconductor industry is near the limit. We can keep shrinking transistors, but we can't shrink atoms." As GPUs approach atomic scale limitations, the pace of performance improvement slows. This presents new challenges for developers aiming to create immersive and complex experiences. The game Crysis serves as a powerful reminder of what happens when software technology outpaces hardware capabilities. When it launched in 2007, the game's engine was so advanced that no gaming computer at the time could run it properly. Even today, running Crysis 3 on ultra settings demands a high-end gaming PC. While the game pushed boundaries, its hardware requirements limited its success, teaching developers a harsh lesson: innovation must align with technological reality. As we near the limits of shrinking processors, the future of gaming will rely on multi-core CPUs and multiple graphics cards. Future systems could look like this. A 16-core CPU with 2 graphics cards, 16 gigabytes video RAM each, provides 32 gigabytes of video RAM and 32 gigabytes of system RAM, 2 gigabytes per CPU core. A 24-core CPU with 3 graphics cards, 16 gigabytes video RAM each, provides 48 gigabytes of video RAM and 48 gigabytes of system RAM. A 32-core CPU with 4 graphics cards, 16 gigabytes video RAM each, provides 64 gigabytes of video RAM and 64 gigabytes of system RAM. As multi-GPU support becomes more common, these setups could handle 4K gaming, ray tracing, and complex simulations smoothly. High-core CPUs would ensure seamless gameplay, as more cores handle background tasks, physics, and AI. Even more extreme configurations are possible, like 64-core CPUs and rigs with 6 or 8 GPUs. These would push performance to extreme levels. To fully take advantage of this power, systems would benefit from technologies like V-Sync on 240Hz monitors. This would deliver consistent 240 FPS in 4K resolution, ensuring smooth, real-time gaming with reduced input lag. For these advancements to become accessible, high-end hardware prices would need to drop by around 70%. With affordable multi-GPU systems and high-core CPUs, cutting-edge gaming performance could be available to a much larger audience. This would ensure that the future of gaming stays within reach.